Endothermic versus exothermic reactions. Understanding energy changes. Endothermic and exothermic reactions are fundamental concepts in chemistry that describe how energy is exchanged during chemical reactions. These terms characterize whether a reaction absorbs or releases heat energy, providing insights into the thermodynamic processes underlying chemical transformations. 1. Energy exchange. Endothermic reactions absorb heat energy from their surroundings during the course of the reaction. This absorption of energy results in a decrease in temperature of the immediate surroundings as the reaction proceeds. Endothermic reactions require an external source of energy to initiate and sustain the reaction, often in the form of heat from an external heat source or chemical reaction. Exothermic reactions, in contrast, release heat energy into their surroundings as the reaction progresses. This release of energy causes an increase in temperature in the vicinity of the reaction site. Exothermic reactions are typically spontaneous and do not require additional external energy input once initiated, as they generate their own heat during the chemical process. 2. Heat absorption and release. In an endothermic reaction, the reactants absorb thermal energy, which is converted into chemical potential energy stored within the products. The energy absorbed by the reactants is greater than the energy released, resulting in a net absorption of heat from the surroundings. Examples of endothermic reactions include the decomposition of calcium carbonate to form calcium oxide and carbon dioxide in the presence of heat. Exothermic reactions release excess thermal energy as the reactants transform into products. The energy released by the reaction exceeds the energy absorbed, leading to a net release of heat into the surrounding environment. Examples of exothermic reactions include combustion reactions, such as the burning of natural gas, methane, in the presence of oxygen to produce carbon dioxide and water, accompanied by the release of heat and light. 3. Thermodynamic significance. Endothermic reactions are characterized by positive enthalpy changes, increment H greater than 0, indicating that the reaction absorbs heat and has a higher energy content in the products compared to the reactants. These reactions require input energy to overcome activation barriers and proceed towards the formation of products. Endothermic processes include melting ice, evaporating water, and many chemical reactions that require heat to initiate. Exothermic reactions are associated with negative enthalpy changes, increment H and LT, 0, indicating that the reaction releases heat and has a lower energy content in the products relative to the reactants. The release of energy drives the reaction forward and contributes to the spontaneity of exothermic processes. Exothermic reactions include combustion, neutralization reactions in acids and bases, and many biochemical reactions that release energy during metabolic processes. 4. Temperature changes. Endothermic reactions typically result in a decrease in temperature of the reaction mixture and its surroundings as energy is absorbed from the environment. This cooling effect is observable when substances absorb heat during phase changes, e.g., melting, vaporization, or chemical reactions that require energy input. Exothermic reactions lead to an increase in temperature of the reaction environment as energy is released into the surroundings. This heating effect is evident when substances undergo combustion, oxidation-reduction reactions, and other processes that liberate heat energy during the formation of new chemical bonds. 5. Applications and examples. Endothermic reactions are utilized in various industrial processes, such as endothermic cracking in petroleum refining, where heat is used to break larger hydrocarbon molecules into smaller, more valuable products like gasoline and diesel. Endothermic reactions are also employed in cold packs and instant ice packs used for therapeutic and cooling purposes, where the absorption of heat facilitates rapid cooling. Exothermic reactions find applications in energy production, such as in the combustion of fossil fuels to generate heat and electricity. Exothermic reactions are crucial in the production of ceramics, where heat released during firing drives chemical reactions that transform raw materials into hardened ceramic products. They are also fundamental in biochemical processes, including cellular respiration, where energy released from exothermic reactions fuels metabolic activities. Endothermic and exothermic reactions are fundamental to understanding energy changes in chemical processes, distinguishing between reactions that absorb heat from their surroundings and reactions that release heat into the environment. Endothermic reactions absorb energy to proceed, resulting in a decrease in temperature, while exothermic reactions release energy, causing a temperature increase. These concepts are essential for predicting and controlling energy transformations in chemistry, industry, and everyday life, influencing the development of technologies and applications that harness energy from chemical reactions for practical and scientific purposes.